So I have two sets here, A and B, and these are the same two sets that we looked at in our example of a Cartesian product back in the last lecture. A is just the numbers 1, 2, and 3, and B are the letters A, B, and C. And over here on the right-hand side, I've written out the Cartesian product, right? All of the ordered pairs whose first value comes from the set A and whose second value comes from the set B. Then what I've done with the diagram here is I've created an arrow diagram that defines a relation on these two sets. And if you look closely, you can kind of see what this is doing. It takes every element of A to an element of B that doesn't have the same position. Right? A is the first letter of the alphabet, so that's the one that 1 does not get mapped to. B is the second letter of the alphabet, so 2 does not get mapped to it, and so on. So how would we define this relation? Remember what I said the definition was. A relation is a subset of the Cartesian product. So every element of the relation should come from this list, and in fact it does, right? I'm going to cross off, I'm actually doing this a little bit backwards. I'm going to cross off the ones that aren't in it. So what's left will be the relation. We don't have a pairing between 1 and A. We don't have a pairing between 2 and B. And we don't have a pairing between 3 and C. So these, 6 points, 6 ordered pairs that are left here, these would represent, right, this particular relation. So I've got another one here, right? This one also defined on finite sets. Right? A is the positive integers 1, 2, and 3, and B is the negative integers, -1, -2, and -3. Right? They're opposites. And I have defined this relationship by x and y are in the relation if and only if x plus y is greater than or equal to 0. So I'd like you to stop for a minute, right, and see if you can't come up with the pairs that are in this relation. So I'm going to approach answering this in two different ways. One way is going to be really kind of algebraic. The other way is going to be a brute force approach similar to what we used in previous examples. What I've done here over on the left is I have written out the Cartesian product of these two sets. There's 3 in the first and 3 in the second, so I came up with 9, just like we did in the previous 3 by 3 example, which is good. That's what we'd expect. You notice how I did this, right? I took the first I took 1. That's the first value of the first set, and paired it up with all the others in the second. Right? It's that same very methodical brute force approach. So what I want to do is I need to figure out which of these ordered pairs has a sum that's greater than or equal to 0, right? And that's pretty easy to do, right? This one does. This one, 1, -2, that would be -1. 1, -3 would be -3. Excuse me, would be -2. 2, -1, that works. 2, -2, that's 0, good. 2, -3 is -1, that one has to go. I'm kind of starting to see a pattern here, right? Following along that diagonal. Down here, 3, -3 is 0. Everything to the left of it is going to have a positive sum. So those, 6 points, 6 ordered pairs, those would be the elements of this relation. Now, if we wanted to do this algebraically, right, I could take this a little differently and say, look, I need x plus y is greater than or equal to 0, right? So what does that mean? That means I need x values that are greater than or equal to -y. So pick a y value. Remember, the y values come from B over here, right? So if I pick -1, then my x values have to be greater than or equal to -1, which is +1. All right, so that's going to be all 3, right? All 3 of them fit that category. So y equals -1 will get paired with 1 2, and 3. And you see that is exactly what happened here in this first column. Right, then we would do it again, right? Say y equals negative 2. Well, that means x has to be greater than or equal to negative 2 or positive 2. And there are two numbers that fit that description, right? Just 2 and 3. And yeah, those are the numbers, those are the pairs that we got right here. And finally, if y equals negative 3, we're only going to get one possible x value. X has to be greater than or equal to positive 3. And yes, there is only one number in A that fits that description. All right, so what are we looking at next? We have one more definition we need to talk about, and after our discussion of functions, it's going to be pretty familiar. We need to talk about what the inverse of a relation is.